Okay.
Hi, we're a couple of team leads from the FSAE internal combustion team. I'm Matt, I'm the team manager and brake subsystem lead. This is Colin, he's the suspension lead. Then we have Alex Luna, he's our chief engineer, and then Alec is our human interface lead. Some background, FSAE is a international intercollegiate design competition where teams of student engineers design, build, and then race small Formula style cars. We compete with teams from around the world every June in the competition in Lincoln, Nebraska. Some of our goals and objectives this year. The goal of this year's car is the goal of this year's team is to design a competitive, reliable car that can place in the top 10 in all of the dynamic events at competition. All of the dynamic events are all of the on-track events where we're actually racing against other people. There's 5 of those. There's acceleration, skid pad, autocross, efficiency, and endurance. Then there are 3 static events, which are the sales presentation, cost, and design report. Most of the requirements for the entire project are set by the FSA rulebook. It's very, very thorough, about 100 pages, detailing safety requirements and all the other requirements for basically every part of the car. And we also have additional requirements per subsystem to help us meet our goals. On this slide, you can see our timeline and work breakdown structure. On the right, you can see our over the fall quarter. That was basically our design quarter. This quarter is where we focus on manufacturing, and the next quarter will be the majority of our testing. In manufacturing, we're a little bit behind schedule due to some problems, mostly with machinists that made mistakes cutting all the tubings for our chassis, and so that set us back about a week or 2. Currently we're manufacturing the chassis. It's about 95% complete, and then most of the major suspension components have been sent out to be machined, and all the other subsystems are slowly getting put together as well. So a couple of progress pictures. You can see on the far right our master assembly with the full aero already designed, which is a big milestone. The aerodynamics package is usually one of the most labor-intensive and time-consuming things to design and manufacture. So it's it's good that we already have the aero kit design. In the middle, you can see the intake manifold for the engine, which is about 75% done. All the individual components have been manufactured. You just have to clean them up and assemble it. And you can also see on the left, on your right, the picture of the chassis. Our budget. The total budget for the car is $24,849. You can see the cost breakdown by subsystem on your left. We've reduced the budget compared to what our original estimates were, mostly by deciding to reuse parts of last year's car. For the competition, we have to make a new car every year. And so we wanted to keep last year's car running, but it was too expensive to do that. So we were able to save a lot of money by reusing those parts, and then we're also saving a lot of money by simplifying some of the suspension components that have to be CNC machined, so that some of us can actually make them ourselves, and just to reduce machining costs in general. We secured about 70% of our funding, mostly through our ZOF funder, which has raised around $11,000 already, and then we also have a variety of sponsorships in-kind donations and also parts and services.
I'm Alex, Chief Engineer. I'm presenting for the chassis. So from last year, we reduced our weight, or we plan to reduce our weight by 20 pounds. Our chassis is about 95% complete, and with just a few more tabs, we plan to meet that goal. Repackage the driver to lowest vertical CG. The driver is at about a 42-degree angle backwards, similar to F1 driving angle. Integrate components that stress members, such as the steering rack and the engine. Now this isn't specified in the rules, but we decided to go forward with this as integrating some of the compressive members or the compressive loads from suspension into the steering rack and the engine to reduce tubing in the chassis itself. Increase the size of the cockpit to allow more members of the team to drive and maintain the torsional rigidity of about 2,000 foot-pounds per degree. So the requirements come from our rules. These are some of the big ones. The main infra roll hoop must be 1-inch 095 mild steel. The side impact structures must be 1-inch 065, and all primary structure of the chassis must be properly triangulated, and drivers must be contained in the primary structure of the chassis. So here's last year's chassis and this year's chassis. As you can see, we have completely eliminated the suspension box in this year's chassis by running our suspension nodes to this 1-inch 095, this is the main roll hoop, and to nodes that are loaded into the engine. We've also reduced the size of the main roll hoop by lowering the driver. So 95% welded, we only have engine mounts to fully weld, and a couple tabs for our subsystem components. Our goal status is we reduce the weight by about 22 pounds. That is going to get a little heavier as we add more components, and the torsional rigidity in simulation is about 1,800 foot-pounds. Once our suspension is fully mounted, we will test that in real life. Our overall CG height has been lowered by 1.5 inches.
So for human interface, the human interface lead, my name is Alec. We had the goal to we set the goal specified in the rules. We had the goals to reduce seat removal time to 20 seconds with 2 people. Design the seat pedal, the seat belt, shifting system around comfortable driving position and lower CG. Standardized shifting and over-the-top shifting and tactile user-friendly pedals. These are the required specified in the rules. So as of right now, the seat and pedal designs have been finalized. The seat mold is going to be has begun manufacture. The brake pedal is manufactured. Throttle pedal is going to be done this weekend. Issues of concern: paddle shifters are coming along more slowly than anticipated, and engine and pedal positions have changed dramatically. So we're worried about how the model will get in the car.
Some of the main goals and requirements for the suspension were to reduce weight by 15 pounds from last year, as well as reduce compliance by mounting the tow arm farther away from the other supports for the uprights. We wanted to, by the rules, maintain 2 inches of wheel travel. We want to have 4-wheel independent suspension, so that rules out some other suspension types. We wanted to keep our motion ratios linear between the wheel and dampers. We also wanted to minimize bump steer that we'd see on the track. So far our progress is that we have all of our parts designed, and they are either designed or selected and ready to be sent out for purchasing. So far we've sent out our major CNC components, which are the uprights and hubs, seen in this picture. And the goals we've met so far are that we're on track to reduce the weight by 19 pounds overall. And we also are meeting some of our other requirements on the suspension. The scrub radius has been reduced from last year, which helps with steering effort. And the motion ratios are also within our desired specifications. As for the electronics, the goals for this year were to add more sensors to allow for more engine tuning as well as telemetry. And we also wanted to manufacture a harness that would be more modular than last year's design while keeping the same basic structure. The requirements for the electronics are to pass all the safety rules, include all the emergency shutdowns, as well as run the engine and log data. The progress so far with the electronics is that the full vehicle harness schematic has been designed, and that 40% of the components have been purchased so far.
So, for aero and body, the goals for the car were to have a coefficient of lift of 2.5 and coefficient of drag of 1.2, and aid in the engine development to have a cooler running engine, because that's all we can follow, and weigh 35 pounds or less. These are all the rules specified within the rule book, and I'm not going to read into a lot of them, but they're basically specifying that the goal of them is to keep you from, creating a car that has too large of an aero package. So here you can see a full car CFD with rolling tires, so that's as accurate as we believe that we can get it. And then the aero and body is again presented on the master assembly to your right.
Just to reiterate, this isn't done in a wind tunnel type simulation. This is the car is moving at 40 miles an hour and the air is stagnant. So we have boundary layer on the floor as well as the rolling tire effect. And for driveline, a large problem we encountered last year was not enough adjustability with the sprocket, the output sprocket on the engine and the driving sprocket on the differential carrier. So we've moved to a shimming tensioning system where we place shims in between this triangulated portion and the circular portion to tension our chain between the drive and the output shaft. Keep our weight the same or less than last year, and these are some of the requirements from the components that we are using and also from the rules and engine output. For engine development, we plan to design an intake system that would flow within 2% to each cylinder. If you're not flowing within 2%, or really the max is 5%, you'll produce less power from one cylinder to the next and create an oscillating power into your crank, which reduces overall power in general. Design a nozzle that maximizes airflow into the restrictor. Implement a cooling system to run the car at 200 degrees Fahrenheit. Last year we ran at about 220 degrees on average for a 35-minute track time. Custom wet sump to reduce engine height in the chassis and produces a sub 4 second. And these are requirements for the engine and from the rules. And these are some of the flow sims that we did in ANSYS for the intake model.
For brakes, so the goals are to make sure that the rotors get up to adequate temperature to maximize the friction they create, and also to have a reasonable amount of effort required by the driver, and also a comfortable amount of travel. Some of the requirements from the rules are that you have to be able to lock all 4 tires at once. That's a big one. They actually test that with every single car. And there's also a minimum forces that it has to withstand. So the progress for the brakes, all parts have been designed or selected, and about 50% of the parts have been ordered. The rotors will begin being manufactured within the next week. So the goals that we met were that we use identical rotors and calipers in the front and rear, which helps reduce the number of spare parts we need. We kept the pedal force similar to what we had last year, which is around 130 pounds from the driver. And the pedal travel is estimated to be less than 1.5 inches, which is also something that we got from last year's car that the drivers felt was comfortable and we wanted to replicate in this year's car.
Any questions?